So we're going to do a quick analysis of volumes of carbon. We're going to be using this unit here, petagrams. That might not mean anything, or maybe makes you think of a pentagram. Not the time for that. But it's actually grams times 10 to the 15th, right? So 15 zeros. This is an example. I think that this was an analysis of a couple of years ago. So these numbers probably aren't spot on for the current year, but they're pretty darn close. So we're going to talk about the major outs, and then we'll talk about the major ins. So the largest source of carbon out, as I mentioned, is photosynthesis. And you can see it's significant, right? 125 petagrams per year. That's most of the carbon out. But the other thing that I talked about is actually the ocean. So the ocean is not quite as much of a sink of carbon as photosynthesis, but it's up there, right? So 125 petagrams tied up in photosynthesis. That actually ties into both long and short cycle carbon, right? So it could end up as coal, or could it just end up as decay right back into the atmosphere? Ocean absorption is fairly longer term. So again, CO2 is highly soluble. And as the increases in the atmosphere, it dissolves and forms carbonic acid in the water. So just kind of doing the basic math, that's 232 petagrams of CO2 stripped out of the atmosphere, essentially photosynthesis and ocean absorption. We're going to find when we look, there's actually far more sources, although hopefully we'll get a number at the end of the day. So I'm going to go ahead and take this 232 and move it over here for later, and then we'll start looking at the sources of carbon in. Okay, so should be no surprise when we look at the largest source of carbon into the atmosphere, it's actually the balancing of photosynthesis. It's the opposite of photosynthesis. It's respiration, right? So remember, again, we had about 130 petagrams stripped out of the atmosphere by photosynthesis. We're putting back about 122 by animal respiration, which is pretty cool, right? Plants and animals are kind of regulating the CO2 content in Earth's atmosphere. So the next kind of large source that we have is ocean degassing. And so again, that has to do with methane created by decomposition of all of the stuff that lives in the ocean. So generally coming out of seafloor sediments, that natural anaerobic decomposition reaction produces natural gas methane, which is really buoyant, and that works its way into the atmosphere. Again, unless the water is so cold that it ends up as a methane clathrate, which, kind of Alaska north, those are the conditions where this would happen. But you would argue that the biological activity in the oceans in warmer areas is much higher, right? So places where you have like coral reefs and things like that, all that decomposition turns into methane. The next one that we're going to look at is not very exciting. So carbon monoxide is something that exists in our atmosphere. And carbon monoxide will actually oxidize to become carbon dioxide, right? It'll bring in another oxygen atom. So the conversion of carbon monoxide to carbon dioxide, about 1.5 petagrams. Now notice these volumes have dropped off pretty quickly, and we'll continue to see that. So 1.7 petagrams of biomass burning. Now that's two sources, right? So we have not only naturally occurring forest fires, which is the majority, but there's also significant problems of burning areas in the rainforest and things where you're releasing a lot of extra carbon. So this can be human or naturally occurring burning, but this aspect of CO2 returning to the atmosphere. So getting really down here to the bottom of the natural carbon cycle, a tenth of a petagram, that's what we call long-term flux tied to volcanic activity. So that's not a huge deal to worry about. And the interesting thing is that volcanic activity is fairly plateaued, right? The amount of volcanic activity that happens in any given year on Earth pretty much averages out. I mean, there might be a large eruption one year and not another, but the rate of volcanic eruptions hasn't necessarily increased or decreased. So that leaves really one thing that we haven't talked about here. And I'm going to go ahead and write this up off of our factory. And this is what we would call anthropogenic carbon. This is the carbon that we took from the long-term carbon cycle, the coal, natural gas, and oil, and converted to energy. And that's actually about 5.2 petagrams. That's the amount of carbon tied up with the energy that we release. So where does this leave us all? I'm going to do some quick math here. So we start to see, well, once we look at these totals, we start to see some interesting patterns, right? So we have our carbon in, 237 petagrams on an annual basis. Carbon out, 232 petagrams on an annual basis. And surprise, that's a difference. And surprise, that's a difference of about 5 petagrams per year. Well, almost everything on this list and this list, we can't really change. Although we're going to talk about a couple of different ways, except for one notable in, which, oh my gosh, is actually just about 5 petagrams. So this system is not in steady state. The system is out of balance, meaning that every year there's more carbon dioxide produced than there is consumed. And that number, the volume of the excess CO2, is just about the same volume as the CO2 that we produce. Then there's also a backside to this, right? So one of the things that we've started to see is actually large sections of trees in the Amazon rainforest, right? We have these deforestation problems going on, not so much here in the United States, but in parts of the Amazon where they've just flattened huge swaths of the rainforest. That actually reduces the amount of CO2 caught up by photosynthesis. So it actually makes this number less potentially over time, but then it produces carbon, making this number higher. So hopefully you guys can see that the carbon cycle is fairly complicated. There's more to it than this. But when we look at long term, we see that it's out of steady state, right? It's not in balance. So what I wanted to take a quick second and talk about before we leave this is how can we visualize this, right? So if we look at the CO2 over the course of any given year, what we see is that the CO2 levels rise and fall, largely tied to this balance, right? Photosynthesis and decomposition. So during the time of year when the trees are really growing, most of our land mass is in the northern hemisphere. CO2 is being consumed, and then when those leaves fall and decompose, CO2 is being put back into the atmosphere. And that's all well and good. But once we start to back up and we look at 5 years, so you can see here, this is 5 years of data. We see the annual up and down pattern, but we also see this general upward trend. And undoubtedly, you've seen this a couple of times, but I wanted to take a look at Dave Keeling's work. He worked for Scripps Oceanographic Institute based in San Diego, but the Mauna Loa Observatory is on the top of Mauna Loa in Hawaii. And the reason why it's out there is to avoid CO2 from plant sources, right? So it's not in the middle of a continent, it's the middle of an ocean, right? There's the small impact of the island itself, but it's out in the middle of the Pacific. And so Dave Keeling started measuring CO2 concentrations in 1954, 1956. And those have increased significantly since then. Like I said, this is not new. You've seen this before. But what you haven't seen before, and what I wanted to tie this together with, is first of all, here is where that's coming from, right? So once we now look at the carbon cycle, we can see it's out of balance. It's not in steady state, and that predicts there's more carbon added each year than there is stripped out. And then we've also been talking about ice cores as this great source of CO2, of historical CO2, because that atmosphere is trapped in those little gas bubbles. So if we look at our youngest ice cores, those that run up to the modern instrumental record, they actually tie in almost perfectly to Dave Keeling's data, like I said, which begins in the 50s. And so you can kind of see in this transition from ice core CO2 right into direct measurement CO2 at the Mauna Loa Observatory, it provides a really continuous record of CO2 in Earth's atmosphere. Like I said, we haven't necessarily talked about methane all that much, but I did want to leave you with the notion that if we think about CO2 as this, 1 part carbon, 2 parts oxygen, and the ability to dance, if you guys remember that, right? We've talked about the strength of molecules. Well, CH4 is 1 part carbon, 4 parts hydrogen. And so if we look here, this is CH4, 1 part carbon, 4 parts hydrogen. It's a really good dancer. So it's actually, its ability to absorb and remit radiation is far greater than CO2. It's a really strong greenhouse gas, although it's not in concentrations in the same way, right? But generally the greenhouse gases in the atmosphere that we think of are CO2 because there's so much of it, and methane because it's so powerful. Okay, hopefully that didn't confuse you too much digging through some of the chemistry. But again, this notion that the carbon cycle is not in steady state is the message, right? That's what I want you to go home with. Well, you're probably at home right now. But anyway, all right. See you next time.